I'm Greg Hertzler. This is something I'm doing with Data 61 at CSIRO part-time, but I'm in charge of getting a nice big report put together. I just talked with Michael, and he's getting a nice big report put together, but I don't have a deadline of tomorrow, so I'm here and he's not. But Data 61 is interested in, somebody thought that was funny, I guess. CSIRO people have a strange sense of humor. 61, of course, is the country code for Australia. So they thought that was funny. But they're interested in big data of all sorts, and my aspect of it is agriculture with them. The title is mostly true. But what I want to do is motivate why I did this, and why I did, the motivation I'm going to give you isn't the real reason I'm doing it, but it's much more interesting to pretend that that's my true motivation. My true motivation is I tend to be a little bit technique-oriented, and this was a great example of something that I want to try to get published. So I sent some of this away to a journal, and they said, yes, but give us an application. So this is my applications. But I'll give you the motivation that I'll try to sell this with. The data, which is basically Bureau of Meteorology data for around Australia. The model I'm going to use, which is novel, the new part of this. And the model is of my own invention. And it does many interesting things, which I hope we talk about along the way. But the main thing that's different from other models is that it actually estimates variability, does lots of hypothesis tests, and all kinds of things. So, null hypothesis. There's climate change. How many of those studies have you seen testing that? Versus the alternate, there is no hypothesis change, or the other way around. So we'll actually be able to test hypotheses. Along the way, we've got to estimate it. And Diana's sitting in the back of the office. I actually got the last numbers in the table this morning at about 7 o'clock. This thing is a bit too intensive to take on the road yet, but I'm working to try to make the estimation accessible and something that almost everybody could use, I hope. That's the goal. Right now it takes a bit of time. Then we'll talk about the conclusions, which are still in progress. I have some conclusions, but we'll talk more generally about Australia, about my preliminary conclusions and what I found. Castle Rock, I guess, for no other reason than that's a picture that I like. I took a picture of that rock, and Dinah said, ah. So she took that picture, and that's the one that was the keeper. So the motivation is, we did a study, Ross did a study for NCARF, and other people spent a lot of National Climate Change Adaptation Research Facility money on projects. Our project was adaptation of agriculture to climate change. We took a new approach in which we were using real options to say, when will farmers actually switch from this regime, which is their main cropping, to the next regime if climate is changing for them? And how did we do climate change? We did it, well, maybe this was Ross' suggestion, maybe it was Peter Heyman's suggestion, maybe it's everybody's suggestion, but we used spatial analogs. So the main application, or the main study that we got published in the Australian Journal was this one with Clare, Oraru, and Hawker. And these are along a climate transect. They cross the Goiter's line here, which is the idea where you grow wheat on this side and you don't grow wheat on that side. And the main idea of spatial analogs is that perhaps Oraru, which is now okay, will end up looking like Hawker by 2050 or something like that. And that's how we're going to say that climate change happens. There are hosts of studies out there using the Ricardian model of climate change. The Ricardian model is basically hedonic pricing of land values. Now, in my humble opinion, there is no climate change in that. What we want to know is, how is the climate changing here? Not how does it compare spatially. It may change completely different differently at Oahu than not. So when you go looking around at weather stations around Australia, you'll find a weather station here and a weather station here, and there may be 2 kilometers between them, and they seem to be on different planets. I'm not really sure that spatial analogs are actually climate change. Okay, the real reason I'm doing this is because this kind of thing doesn't fit what I want to do, which is do option pricing and all kinds of fancy mathematical stuff, and the spatial analogs doesn't work for me, so I'm going to do something that does. That's my real motivation. But this is the public motivation for why this is. We want to actually see in a location where we're going to adapt, how is the climate changing? And then put that into our decisions. The data I'm going to use is just off the website of the Bureau of Meteorology. The goal is to do 17 weather stations around Australia which have long-running time series. These are in the Australian, the ACORNSAT data, ACORNSAT network, but it's not the homogenized data. This is the raw data we're going to use, not the homogenized data. Okay? So these are referenced stations where the documentation is about as complete as you can get. They all go back at least to 1910. There are other stations around Australia, probably some in the wheat belt we'd be more interested in. They go back a long way, but the documentation I'm not too sure about. Okay, at least we'd have to work at it. So 17 is a big number, and I just picked these out because they were in the reference network. No other reason, really, long running. Maybe they're not the most interesting for agriculture. Most of them are along the coast. A majority of them are. A few of them are inland. Marble Bar is by far the hottest place in all of this data set. It's also the least variable by a long way. Cape Otway is a wild place. I wanted to show you results for Cape Otway today, but it is so highly variable it takes 2 days for my thing to converge, and I just didn't have time to get all the estimates out. So it takes me a week to estimate this, and this one takes 2 weeks. So I'm going to show you Cape Leeuwin, which I thought would be a very, very interesting one. Turns out nothing much happens down at Cape Leeuwin. But it's closer to home. And others around the place, like Wandering, have some funny things going on. So there are interesting things going on around the place, just looking at the data. But today I'm going to show you Cape Leeuwin and demonstrate what I'm up to, and then we'll talk about the rest later. Okay, so we'll come back to that one. The model, it was Dave Pannell told me, for every equation in your presentation, you lose half your audience. He told me that a long time ago. And I mostly believed him. What I wasn't too sure is what happens if you have an odd number of people in your audience. And I forgot to count how many before I put this equation up, we should count how many people, because bad things could happen. And by the time you put 2 equations, then suddenly you've got 3/4 of a person here and 1/4 of a person there. So I'm going to put some equations up. Just be warned. So we're going to use this thing called the generalized Ornstein-Uhlenbeck process. It's not too crazy. The thing that I've done is put trends in location and scale. Now that sounds completely, but it's not too hard. And you can think of this process as containing, okay, if you go to the library, there's this blue volume by Johnson and lots of co-authors, 3 volumes of continuous probability distributions. This has about half of those as special cases. There's another one that has the other part of that volume of special cases. So this isn't a specific thing. This is a very general way of going. And in my world, everything happens with time in it. And this is how in our case, temperatures are going to change over time. This little bit here is how we expect them to change. This is the error that goes on the end. So G is the instantaneous mean, it's called. And H is the instantaneous, in this case, standard deviation. And dB is, in this case, Brownian motion. You don't have to assume Brownian motion, but probabilities are all special cases of Brownian motion. Most people think Brownian motion is a bad thing, but everything we do is actually a special case. So we start with this in my world. Everything changes over time. And this is how temperatures will change. I've used Z instead of T for temperatures because in this world, temperatures have two things that happen. One is the current temperature we observe, and then what we are expecting for the future. So in this world, we ask the question, what's the chance of rain? Now, in a world where there isn't time in probabilities, you can just answer that. So if you have a deck of cards and you say, what's the probability I'll get a queen of hearts if I turn this over? 1 in 52, is it? I don't know. I'm not a card player. Oh, yeah. So it's conditional. Yeah, so these probabilities are conditional on what's in the pack. But suppose I shuffle these, and then I ask, what's the probability of the queen of hearts? It hasn't changed. But if I ask you, what's the chance of rain, or what's the temperature going to be, you have to put it into context of what's the temperature now, and how far in the future are we looking. Probabilities make no sense in this framework unless you put time into it. You look and see what it is now. In a nanosecond, it's going to be a lot like it is now. Tomorrow it could be something else, and next year, who knows? So the probabilities all depend upon the current temperature, what time it is now, and how far in the future we're looking, and then the probability of the temperature tomorrow or the next day or in 10 years is a function of 4 things, actually. So we're used to probabilities that are functions of y. This is a function of y and x and t and s. This is the Ornstein-Uhlenbeck process, which converges to something. Some of you may be interested in arithmetic Brownian motions and geometric Brownian motions. I'm sure nobody in this audience is, but everybody in finance is. So you go to finance and geometric Brownian motion is everything. It explodes, right? And so does arithmetic Brownian motion. And they're the ones that are the main uses in finance. But this one actually converges to something, and what it converges to is this. But that's kind of boring. The temperature never just converges to some number. It depends on what time of year it is. It depends upon what it is today. It depends upon all kinds of things. So the novel part of this whole exercise is making the things that it converges to functions of time. If we were doing a normal OLS, this would just be some f of x is the mean kind of thing. So most people just think of that as the mean, but we're going to think of it as something more complicated. The standard deviation also is function of time. In a technical paper, I have lots and lots of proofs. I won't go through them today, but out of those proofs comes the likelihood of a sample. So we're going to use this today. This looks just like any other likelihood so far. E to the minus 1/2 and a few things there. This thing is the residual, and y is the random variable, g is the mean, and h squared is the covariance. We're taking the square root of it, but that's just a residual, weighted like we'd see in ordinary least squares. The problem is that the mean is that function, and the covariance is that function. And so they're big and ugly. They're integrals over time. So the mean of the temperature that we expect to observe depends upon S, which is today, right now, this instant. T, which is how far into the future we're looking. X, which is the temperature now. And so what we expect to see tomorrow depends upon the temperature today and the time today and the time tomorrow. Okay, and
so why is today's temperature being discounted?
Okay, this thing is not a discount rate.
No,
Yeah.
No,
It's the rate of convergence.
Yeah.
Okay, but well spotted. What it means, suppose that t minus s becomes really big.
Yeah.
We're looking a long way in the future. So what's the temperature next year? 1 year from today. Well, it has
This
no...
information has no value.
Yeah, today's temperature tells you nothing about the temperature a year from now. So this tells you how fast the information in today's temperature disappears from the...
So it's a discount.
Yeah. But it's the rate at which things converge. It's an estimated parameter that we're going to actually estimate it.
So we have a sample of temperatures
Yes.
observed over time,
Yes.
and the likelihood function is the likelihood of what?
Okay, so in the data consists of the date and the date of the next observations. So the data is actually, this observation is observed on the 1st of May. This observation is observed on the 10th of May. This was the temperature on the 1st of May. So that's the data. No?
It's trying to capture, I think, the idea of autocorrelation. That appears in turbulence, like high frequency stuff. So that means that tomorrow's temperature will be related to today's, but that will gradually weaken in the future. And there's a few functional books that's trying to capture that bit.
Yeah, except, well, that's this bit actually. So correlation goes with covariances. And these are also discounted. But yes, the information today disappears from the probability if you're looking a long way into the future. And it disappears at this rate. Okay? And so you can think of that as a disappearance. I'd call it a convergence because it has nothing to do with interest rates or anything, or human preferences or anything. It's just the nature of temperatures.
H squared is also volatility.
Yeah, you can. I'm not sure what. Hello, is H squared volatility? Volatility means different things to different people. But yes, I just call it the covariance, just because I do.
It's covariance with what?
Over time.
So it's an auto
Yeah,
covariance.
it's autocovariance. Yeah, and which leads to autocorrelation. Yes. And the hard part of these is that they're integrals, and you have to estimate an integral equation.
So where is this for one location at a time?
One location at a time. Now, okay, so you could put all of the weather stations in Australia in this thing all at once and estimate them, but I'm not that good yet. But there would be correlations between locations as well, and I'm assuming those are missing or zero.
So why did you decide to go through the continuous time approach rather than just using a Garch model?
Okay, another good point. There are other approaches to time series. I grew up doing ARE-UWA models and Arch and Garch models. I was doing Arch before it became Garch. And all of the interesting stuff is taken out in the differences. I mean, all of the interesting stuff disappears from those models.
Yeah, you assume stationarity.
Yeah. And so you take the differences to get them so that, and those differences are the trends that you're actually interested in. So it takes all the interesting stuff out. There's another way to do time series, which is to just do the trends. It also assumes stationarity, and I'll say in a bit that I think that's a drop-dead dumb thing to do. But those are, so I'm a little bit more aligned to the simple-minded one, which is put in a trend and see what it looks like, and we can interpret the trend. Yeah, so I'm not in the Arch-Garch world. But of course they've expanded on that a lot, and you can do all kinds of things with trends and other things in there now. But I just think they started, well, stationarity I think is just not a good thing. But that's the real reason I'm not doing that. Okay? Is that, you're saying yes, so I guess I can move?
Yeah, yeah,
Okay, so we're going to estimate these integral equations. There is one problem, one big problem. And so suppose I just want to estimate an exponential trend. So this would be a function of exponential growth, say, or exponential decay. So when I started this, I wanted to estimate the exponential growth in temperatures because that's what I expected to find. Yes? So I wanted to put this exponential growth into the estimation. This is really just an intercept or a scale factor. This is the rate of growth in temperatures. And this is just a time for when you might start the process. So you have to start this growth from someplace. So I started it at 1910 when official records began. But the real interesting thing is, what's this rate of growth? Okay, the problem is, you put this rate of growth into this equation, it interacts with this discount rate, this rate of convergence. You cannot estimate the stochastic process and the deterministic trend separately. And you integrate that and it comes out looking like this. Mostly that's just to impress you, but it has a time trend in time, which is the future time. It has a time trend in today's time, which is today's time, but it's not as big as the other one. So I'm only putting this up just to impress you. So how many quarter people do we have now? By the time
48.
we're 148.
We're down to 1 in 2048.
Well, now it's going to be 1 in 4,000. I think it's 1 in 4,096 or worse. Yes, because I want to do cycles, right? You're looking at temperatures. There are annual cycles. You cannot do cycles, but they're all. And this is what I came to kicking and screaming because I didn't like this. But I can't actually get the model to estimate without longer cycles. It just won't estimate without longer cycles. So I put this up to impress you. You integrate that one, and it comes out like that. And I've got many of these in the model. And they're kind of slow to calculate, so that's why it takes so long to calculate this thing. So I'm just putting it up to impress you that you have to estimate the stochastic process that you are interested in, plus all of these deterministic time trends that you're interested in, and you have to do them together. Now, if you assume stationarity, basically what happens is you cannot estimate the rate of convergence, and I don't have it on here, but you also cannot estimate a variance or covariance. You cannot distinguish between a very rapidly converging process, which is very volatile, and a very slowly converging process, which is very stable. You simply cannot tell how the weather changes by assuming stationarity, except for the deterministic trends. So that was just to impress you and say why it takes so long to estimate this model. There's another problem with those equations in that this model is, it's like climbing, I don't have my mesa, I should have my mesa up here now. It's like climbing that courthouse, that picture that I showed you. Very steep to get up to the top. Once you get to the top, it's flat. And most algorithms just can't do this. So I tried using normal algorithms for maximum likelihood, and they just don't work. They never find the answer. So the problem is that these trends can all converge to a constant, and you can just end up with huge problems. If you were doing matrix methods, you'd have massive multicollinearity, and it would just blow up. Your computer would blow up. So it's hard to estimate and slow. But other than that, it works pretty well. So the estimation I'm going to show you, I'm just going to give you the taste of the results for Cape Lewin. And I'm just going to do the minimum temperatures because we don't have a lot of time. And the data looks like that. I've squished it all in together so it looks kind of... but how do you pick climate change out of that by looking at it? I don't know. How's the climate changing in Cape Leeuwin, the minimum temperatures? What do you reckon? Well, I don't know.
Well, would be strongly influenced as a virtually maritime site, so I wouldn't expect the minimum temperatures to change very quickly at all. Most of the changes, the trends we've seen have been land temperatures as much.
Yeah.
The ocean's heat capacity dampens that a lot.
But so that's why Cape Leeuwin is not a good example. But we go down to Cape Otway, things are different. I mean, that place is wild in there. It just, I didn't have time to estimate it. So some of the maritime ones have changes. The land-based ones are much more variable. The ocean-based ones much less variable. But you would think that if there is climate change, the ocean would be heating up and we'd all be getting warmer, right? Sorry?
Well, if you've chosen all your examples from 300 kilometres in from the coast, it'd be a lot wilder than we've got there.
Yeah, so wandering is one of those.
Yeah.
It's got the wildest minimum temperatures imaginable. Hard to estimate, but I'm working on it. And that would be a great place to do weather derivatives and things. So,
Well, that's what the farmers are having to cope with. Rather
Yeah,
than
so-
fishermen might have a different view of it.
yeah. So the reason for doing the coasts, I have to just say, is the weather. The data's better. I have to just say that's the real reason. The data's much better, and there's lots of them along the coast with long-running data series. And the real question is, how's it changing over the very long run? I'm not so interested in the wild bits in the middle. How's it changing over the longer term? This is the estimate of the mean and the covariance, just to say that you can do it. It's still hard to tell much from that. One thing that these little peaks aren't a mistake. What happens is you don't have to have evenly spaced observations here. You can have observations 1 day apart. You can have observations 10 days apart. And as the observations are further apart, the variance is higher, just because that observation with a wider space has a higher variance and is less important in the estimation. So it automatically discounts or takes care of wide-spaced observations. Here is a glitch in the data. That's not my mistake. Somebody took the variability out of the data in that period. They just took it out. I don't know how. It's gone. So you have to, this is raw data, not homogenized data. And you just have to, I haven't found too many of those, but you find things. And the documentation for what they did is not there.
Oh, well, I'm just trying to say there should be metadata for that, because it almost looks as though there was a site change for a while.
Okay, here is the beginning of official records. Very good point. Here is a small move. Here is the automated weather station. Here is another small move. So between the small move and the adoption of the automated weather station, somebody did something. And it wasn't the site. Somebody did something.
One other potential source of error is, assuming that we're still manual observers,
Yeah, to here.
you can get systematic errors if an observer is rounding up or down with temperatures or that sort of, because they're still reading like a vernier scale.
Yeah.
Thermometers, so that's
Yeah.
a possibility.
Well,
Which means that some values are not likely to occur because the
yeah, but
observers rounded them out.
these guys did differently than this guy, right?
Yeah.
Different observers.
Yeah, that must sound strange, but that's what the case happened.
Yeah. So, okay, so that's the kindest interpretation. The reason, well, some of these weather stations are labors of love by people over a long time at the post office, right? This probably was too. But the reason for putting these documented breaks and wanting to know is because if you don't get these changes in the weather station properly accounted for, you could be thinking the climate is changing when it's just the weather station. So So I'm trying my best to take those effects out. And this one we definitely have to adjust for, or you just get a weird answer. Okay, I'm not going to go in too great a detail through this one, but what I want to point out is here is a long-term trend, which is some of those trends that I told you about. And that's this thing. Add an annual cycle to it. This doesn't look like an annual cycle, but we're going from 20 days before the end of December to 10 days into January here. And this is what the estimation looks like for 30 days. Okay, so this is an annual cycle, and over those 20 days doesn't look like much. But we have all of these trends and annual cycles, and this is the covariance. And the thing to point out is this is the last observation in my data set. What happens? The next observation starts converging, and it converges very, very quickly to this trend. And that's because this is a very rapidly converging process. It just converges like glue, which is disappointing for me because what I wanted was some nice, long, slow convergence to say that you really need to do my technique because the other techniques will give you a bad answer. But you could almost get this answer without all of this fancy stuff. The one up the top is the mean. This is the mean. And the way the mean works is here are the observations. Okay, the last data point is here on December 31st. And we're going to use that and compare it to the mean on December 30th. And the mean on December 30th is here. And that minus that gives us a residual. And then we're going to divide it by this covariance and end up with a weighted residual, and that's the basis of the estimation. The mean in this is always between the observed data and where this thing is converging to. So it's converging to this line, and the mean is always between the data and that line because it thinks that we're going back there, right? It doesn't think we're exploding and heading off someplace. It thinks this is a weird observation and we're actually going to end up going back there soon. So it converges back to these trends. That will let me use these trends to talk about climate change. I'm just showing this to say here's a residual, and we're going to have more residuals on the next page. But the adoption of, this is the official start of the data in 1910, January 1, and they standardized the sunscreens and a few other things. I'm not sure, but the sunscreens became standard, and you'd think that could have a big effect on temperature measurements. It turns out in this data set, accounting for those shifts in the weather station, it had no effect at all. Maybe they had the screen in place earlier. I don't know. So this was a non-event, really, the switch. Here is the adoption of the automated weather station. And there was some shifts in the variance, but the mean just kind of carried on. So it wasn't a big effect either. Cape Otway, which I've looked at, has like half a year worth of mess after the adoption of the weather station. They really got it wrong in there. So you do have to account for them, but this is a pretty well-run weather station, I'd have to say. I don't know. Just looking at the data. Okay, so those shifts are here. What I'm going to be interested in is this long-term trend, which includes exponential trends, long cycles, a constant. And here is the covariance running along here, trends in the covariance. And those shifts in the weather station had very little effect here. It just went very smoothly. So if it didn't go smoothly, this would take a big jump and there'd be all kinds of mess at that point. Here's the maximum temperatures. So minimums were by an alcohol thermometer, right? And maximums by a mercury thermometer. They could be very different things. And the switch to the maximum temperatures was much more eventful, even though it's probably they're right there together, I suppose. So I'm not sure of the explanation for that, but that's what it says when we tease it out. Okay.
Oh, yeah, it looks like there was definitely a metadata story in either the observer or with the instrument.
Yes.
Somewhere.
Something, I'm guessing it was with the instrument or something, but who knows. Or maybe they just got up late and didn't measure till 12 instead of 9, or I don't know.
Well, see, assuming that's just a straight maximum temperature. There's a little slider in the mercury glass that stops at the maximum temperature. So when you come and read it, it doesn't matter so much. It's captured just when that was.
Oh, okay, okay.
But you will get slightly different results compared with the electronic measurement because of longer, it's sampling rates, that sort of thing.
Yeah, well, here's the electronic measurement starting here, going from here to here. They moved the side a little bit, and it had an effect. And I'm sure it was the same instrument and the same everything. It's just a side effect in that case. So those things are all rolled together into these dummy variables that I put in. Okay, what I want to ask is climate change. How do you do that from all of these ugly things? What I'm going to do is basically take out these shifts in the site, ask the question, suppose the current weather station at its current site had been measuring since whenever, by taking out those shifts. And the minimum temperatures would look like this. Now, this bottle brush thing is just the annual cycle. And this is an exponential trend, a long cycle, and a constant just to shift it up. This also is an exponential trend and a long cycle and a constant. And here's maximum temperatures. And they don't quite look the same. All right? So the minimum temperatures were going up here in covariance. These are going down. And that's doing funny things. And this is probably why this is not the best weather station for my example. The data is good and it estimates nicely, but here is the numbers then. So those graphs translated to numbers. So the maximum temperature, the numbers on that graph, started in 1907 at 20.1 and 2019 20.36. These are the numbers in between. I've taken the liberty, as any fool might, of projecting this on to 2050. I mean, this is a mug's game, right? Nobody in their right mind would do that. But that's what we want to know, I guess. And then this is the minimum temperatures. And as you can see, and this seems to happen everywhere, it was colder in the middle of the last century. And colder here. So the changes we're talking about now are much more dramatic because we're starting off of a lower base. The projections to 2050 are a mug's game. I think you can come up with all kinds of projections based upon how you tweak the parameters. Okay, the other question, and probably the thing that's more unique to this study, is I've called it scale, but basically I've taken the square root of the covariance trend. And so this is like a standard deviation, so more or less. And if you divide the standard deviation by the mean, you get a coefficient of variation. So this is like an absolute measure of the standard deviation, not the variance. And this is like a relative measure that you could use to compare minimum and maximum temperatures. Cape Lewin with Wandering with Marlborough Bar. Okay? So I thought this was kind of interesting. I don't know if it is or not, but I thought it was. And what happens when you do this is that minimum temperatures are more variable in relative terms, scale compared to mean, compared to location. Location just means mean, and scale just means standard deviation, really. And that seems to be happening most everywhere, that minimum temperatures are more variable.
It's because it's sensitive to the mean of scale. If you start from zero, absolute zero, you have different.
Well, that's a bigger question than this. I mean, what is actually a temperature?
Suppose you start your zero with 100 Celsius, you would have higher variability here.
Well, this is, yeah, suppose the mean was 0. I don't know what happens when you divide by divide by 0. Any variability is infinite. Sorry?
Measure everything in Kelvin.
Yeah, we could, but we don't. And it would just be adding a constant to all of these numbers. So. But what is a temperature, actually? It's not really a measure of heat, it's something else. Okay, so 2 lessons here. Temperatures were less in the middle of the last century. In relative terms, minimum temperatures are more variable than maximum temperatures, seems to be. And I think that also goes across space, but that's yet to be determined. But hotter places seem to be less variable than colder places. And then the projections here are irresistible, but don't take them too seriously. Is it really going to be cooler in 2050? According to this, we're going to have a peak in about 2035, and it's going to get cooler. And this is going to continue to get more variable, because as it gets cooler, it gets more variable. Now, that flies in the face of everything I've been told. What do you think? The parameter estimates I'll go through quickly just because we don't have a lot of time and we need to move on. I've accounted for the changes in the weather station so that the estimates of the mean and the covariance aren't messed up and you think that the climate is changing when it was just the weather station. This is a pseudo R squared that was calculated, but that's really like the portion of the variation in the sample that was explained. 40,000 observations in this one, 33 parameters. Other, Cape Otway has like 56,000 observations. So with that many observations, you can test any hypothesis. The rate of convergence is 247. That's in days per year. If it was a normally distributed system, which we all assume in all our estimations is normality, this would be 182, which is half of the days in the year. This is much, much faster converging than a normal process. So if you try to estimate this with arch-garch, assuming normality and stationarity, you just get the wrong answer, really. Okay. These are all of the parameters. These up here are the changes in the weather station. This is just a constant where it starts. Here is an exponential trend with a rate of growth in the exponential trend, which is the interesting thing. Here is a long cycle with its amplitude. That's degrees from peak to the middle. And then the peak to the trough is twice that many degrees in the long cycle. The cycle is 138.8 years long, and it starts in 1896. So the next peak will be 140 years, about 2035 or so, for this long cycle in location. The annual cycle is taken out, accounting for changes in weather stations and other things. And an amplitude. So from the middle of summer, halfway through, the temperature drops by 3.14 degrees, and then it drops another 3.14 degrees going into winter. This is the variability. Now, this is in terms of degrees centigrade squared, so it's like a covariance. And it's kind of uninteresting, except to say that there is a long cycle. This is that big coefficient that accounts for that funny-looking data that we saw. So here is the amplitude of the cycle. Here is what you have to subtract. So almost all of the variability in the data was taken out by whatever happened at that point. And the model accounts for that. These are the p-values. And what you can see is that null hypothesis, this coefficient, whatever you say, is 0, and that's the p-value. So if we say the long cycle, the amplitude of the long cycle is 0, the p-value is pretty small, so we can reject the hypothesis that there is no long cycle. We can't reject the hypothesis that there's no exponential trend. I mean, this is explained by a cycle and not a trend. The same is almost true here, but the variability doesn't seem to be changing at all as per Ian's instructions, I think. Okay. So you can test hypotheses in this. And moving on to my conclusions. No climate change at Cape Lewin. I can reject that one because there is a long cycle. No change in the climate variability. Cannot reject that one, actually, at Cape Lewin. I'm sure at other stations we will. Other stations are much more interesting, I think. Okay, so just quickly about what I found in preliminary stuff running around the country. This place is wild. This is the place I should be using as my main example because all kinds of things happen there. Very, very highly variable in winter and summer. Wandering, and also it has a very long data set, which could help tease out these long cycles. Now, don't take these long cycles as anything gospel because we don't have enough data to know. I mean, we've basically got one or less observation on this cycle because the data goes from 1870 to now, and the cycles are that long or longer. Sydney is an interesting one because there's no drop in the temperature during the middle of the last century, but that's because they were building this bridge right next to the weather station. And so there's urban change in Sydney, which is interesting. Moruya Heads is interesting. There's another weather station just inland from it, not very far, just there. This one still uses thermometers, last I looked. It never had a change in the weather station, and it just looks like nothing happens there, but it's unique in that way. Wandering has these wild minimum temperatures. Marble Bar is the hottest and by far the least variable. So when we look around these places, I think what we'll find is that the temperatures mostly declined in the last of the previous century, and the variabilities basically are opposite to the temperatures. Hotter is less variable, cooler is more variable. Okay, so two ticks. I just have all of these things that I want to use it for. When I speed it up, I'll try to get other people to use it. Right now it's a little bit frustrating, but I think it can be used in all kinds of ways. Anything you might be interested in, environmentally or economically or otherwise, I think it can estimate things. And this is the one that that really motivated me because I thought we did an adaptation to agriculture under climate risk study and it didn't have any climate risk or change in it anyway. So I want to put it into those kinds of things. I'd like to do sea level rise. There's good data for that one. And I think this model will apply directly. I'm not too sure how to go about this one, but it seemed like an interesting thing to do. Okay, so I've run over my time.
Thank you.